Welcome, everyone. This is our fifth Science and Conservation event of our 24-25 programme. What we're going to do is have presentations from each of our panel, and then we'll have time at the end for Q&A. And we have a really extraordinary panel. We have three luminaries from inside ZSL. We have Paul from the zoos, our senior curator, Invertebrates and fish. We have Chris from our Institute of Science. We have Rachel from our Conservation and Policy team. And then we're very honoured to be joined by Sir David King, who is a towering figure, not just of UK science, but of the global hinge between science and policy in a way which I think is profoundly important to the subject that we will be discussing through the evening. One of our panel, Paul Pearce-Kelly, has I think a rather lovely habit of giving me lots of reading to do. Particularly before it turns out, I'm not sure if he does it on purpose, but before I go anywhere on holiday, I often get a thick tome from him to study as homework. One of the thick tomes that Paul gave me was the big global report on tipping points. And I did read it, and it was terrifying. And I'm really pleased we are thinking about tipping points this evening, because it strikes me as somebody who spent most of my life in the policy world, we suffer from many cognitive biases and weaknesses, but one of them is an instinctive feeling that the world will move in a linear fashion. And we find it hard as individuals, as countries, as policymakers to properly take account of the risk of catastrophic shifts. And the problem is not that we are at risk from catastrophic shifts, but we are watching them unfold in predictable and predicted ways, and yet collectively we still haven't managed to sound the alarm loudly enough or convincingly enough to elicit the response that these shifts require. So I hope this evening we will both hear from our speakers about the science and some of the impacts of the tipping points that we're describing, but we'll also be able to get on to what is required from us as people who care about nature and the future of the planet, as scientists, as conservationists, as people involved in policy, from organizations like this one and from countries like ours. So I think we have an important and extremely interesting evening ahead of us. Our first speaker is Paul, who's taken a break from finding me things to read to speak to us. One of the great pleasures of my time in this job was giving Paul a certificate for 40 years of long service at ZSL. For me, in lots of respects, he is a personification of what this organization stands for. Deeply expert to an extraordinary degree, utterly committed and passionate in the best sense about what he's trying to achieve, principled and brave in how he addresses subjects, but approaching everything with a kindness that all who know him will recognize and appreciate. His influence has stretched well beyond the boundaries of this organization to the international efforts around the protection of coral in particular, partula snails, numerous other species, but more than that, to the institutions, particularly in the IUCN, which are coordinating so many of the important efforts to which we are contributing. We are really lucky not just to have Paul speaking this evening, but to have Paul as a core member of the ZSL team. So, Paul, over to you.
Thank you very much, Matthew. It's much appreciated. So here is an actual copy of the recent endeavour that one's been involved with for the last few years, couple of years. Don't worry, I'm not going to stand and read it out. I've only got 12 minutes, so I just wanted to kind of use this opportunity to introduce you to the concept of tipping points, take you through some of the initiatives and what I've learned from the engagement with the process, and in terms of what I think are profoundly important considerations that are relevant for every citizen of the planet, never mind the conservation community. So this affects us all. That's why I'm keen to go through it in that manner. So again, I just want to take us through some introduction of some major revision initiatives, which is largely the Exeter University-led Global Tipping Points revision, led by Tim Lentin and the wonderful team at Exeter, working with international collaborators, a big endeavour. I learned a lot from being involved with that process, predominantly looking at coral reefs, but we're not going to talk about corals because my colleague Chris Yesson is going to give us a good actual insight to those. I'm going to go try and through some of the principal findings, how the actual evidence is utilised, some interacting stresses and cascade considerations. And I must stress, these are my own views. I'm not representing an organisation, Exeter or anywhere else, or even a formal report. I'm sharing what I really feel are important elements for us to consider from this tipping point perspective. So, and before we go into tipping points, of course, we all know we have a full-blown on biodiversity crisis. Thank you very much, with all the traditional stresses we have to contend with. So there's no shortage of extinction options in terms of what biodiversity is facing. And of course, this all chisels away, whittles away at the resilience of these systems. So they are that much more compromised when there are big system changes that they have to contend with, not least climate change, of course. And we're all familiar with, I think, the larger kind of system-level reviews like planetary boundaries. Most people have heard about that, I think, in terms of that. They're not tipping points, but they're very kind of relevant to these kind of higher scales, largely focused on keeping a healthy, functional system that can still provide the critical services, etc. So a different thing, but very relevant. But tipping points themselves as viability thresholds, again, it's not a novel concept. They've been around a long time. It's absolutely in the IPCC, the UNFC, the actual climate conventions, major outputs and threat assessments. And again, hiding in plain sight, perhaps, making really important statements about whole systems going into exceedance in terms of thermal exposure, etc. So again, not a novel concept. It's out there for anyone who wants to look. But back to the Exeter initiative, again, with the Global Tipping Points revision, I thought it was such a timely, valuable thing, and I was, again, pleased to be able to collaborate on it to a degree with corals and coastal systems, and seeing some of the wider discussions. Again, just introduce colleagues to that. One of the things important that they define what a tipping point is, of course, and you can see here, they define as occurring when change in part of a system becomes self-perpetuating beyond the threshold, leading to a substantial, widespread, frequently abrupt and often irreversible impact. And this definition does include the possibilities of non-abrupt and also reversible tipping points. And a tipping system is any system that can pass an actual tipping point. So again, findings that out of that evaluation process, there are 6 cryosphere Earth system tipping points, 16 biodiversity tipping points, and 4 ocean atmosphere tipping points, all varying degrees of vulnerability and exposure. How the assessment process goes through, you're trying to look at key drivers, the stresses, if you like, how they all feed through in terms of their impacts, and where the critical thresholds may actually be for those. Could be temperature, could be drought exposure, could be rates of sea level rise, etc. Again, I won't go into it because you can see all this in your own time. And I'm sure colleagues may have heard about the concept of interacting tipping cascades. So something bad happening in one system being tipped can affect other major systems. ecosystems, usually in a bad way, but not exclusively, potentially. So here, good example of that, the classic one is how Greenland actual ice sheet melt freshens the actual North Atlantic Ocean, which in turn affects big Atlantic meridional ocean system currents, which in turn can affect precipitation dynamics over the Amazon rainforest and lead to things like Amazonian dieback, forest dieback. All of these things are there. So this kind of how systems are connected becomes increasingly important. And again, I'm sure that people may have heard in the news recently about the big concern over the AMOC, this big North Atlantic ocean current change is becoming much more sensitive. So again, iterative review becomes essential. You can see the associations, but what's actually happening on the actual on the ground becomes important. And if you read nothing else in that report, look at page 77, because it really does help to highlight what I would consider, where you can see these range of potential. You could potentially have a Greenland ice sheet free of ice at 0.8, but much more likely when you get up to the higher levels, maybe 3 degrees. So these are all considerations of what might happen for associated sea level rise, etc. I'm find it a bit hard to get my pointer to work, but let's just, but if I'm thinking, my takeaway to that was, if I'm a policymaker, I'm living on the coast, I don't need Greenland to provide 7 meters of sea level rise. I need it to provide 1 meter with other cryosphere impacts, and I have an unmanageable situation as far as those coastal cities or ecosystems are concerned. So you could almost look at it, the sensitivities within the sensitivity. What does it mean from, practical, real-world consideration? And I think these are key risk policy issues. Not just, oh, well, the whole system may be resilient up to a certain level. How sensitive does it have to be before bad things result from it? And I think that we see that within these greater sensitivities, particularly when you're looking at things like sea level rise. And we've got to take into account, again, these aren't just dry desk exercises, what's happening in the real world. We have a truly awful situation in terms of emissions control and actual trajectories ongoing. The last emissions gap report showing how dire it is and what high levels we're heading towards. The rates of the magnitude of greenhouse gas concentrations. Look at our current policies, pretty much committing us with almost certainty to go past 1.5, past 2 degrees on our current policies. So these are reality checks we need to take into account. And these matter hugely. It's not just temperature dynamics, but of course greenhouse gas concentrations will determine things like how much stress we build into the system, how much ocean inertia there will be, what the eventual warming levels will be, etc. And then the sensitivity findings seems that we're finding a much greater levels of sensitivity presenting. We have Earth's energy imbalance having been doubled, statements from NASA, and seeing a large literature around that. Latest findings on the acceleration of warming, ocean warming, etc. You probably heard about the effect on terrestrial system sinks over the last year has been greatly compromised. And if that becomes a longer term trend, major serious stuff. So being on top of these kind of reality checks, what's actually happening, will all come back to how you evaluate the resilience of your system. And I just put this in because this was produced very recently showing that, again, the socioeconomic dynamics, the impact on GDP has always been thought to be quite modest, even under very high kind of climate impacts. But this major review has blown that out of the water, and the impact on this really affects society's ability to cope with stress and to manage things. So these are major socio-economic resource considerations. And you've all got to take those into account when you're trying to evaluate your coral reef or Amazon rainforest, whatever it is. So our slow decarbon process is just awful, as Tim pointed out, 7 to 10 times too slow at decarbonizing the actual economy. This brings us stark reality into overshoots, and the concept of overshoot from a climate perspective is you're trying to go for, say, 1.5, but you may go over that for decades, maybe out toward the end of the century. If all efforts are made, you may get back to that kind of level. But you have ecological overshoots as well, and they're working in concert. And again, there's a great concern about the reliance on that, how safe a strategy as that. And again, there's a lot of kind of thought now that we need to be very careful about thinking that you can have these delicate systems, particularly with these sensitivities really presenting, being a viable future strategy. And that brings us into, well, again, what can we do about it? Can we actually, what can we do to draw down CO2? What can we do to get out of the incredibly dangerous trajectory that we're currently on? And I actually put Sir David King up there, giving a fantastic overview to some of these specialised areas, which I really value. But there are lots of potential things that really need to be investigated and pressed. Can we utilise these things? What is out there for us to really get off the trajectory we're on? Because we are not in a good place. So I think situational awareness becomes super important in its broadest sense, being aware of all of these wide dynamic stresses, their interacting nature, actually what we're doing about it, the trajectories we're on. We've got to take that all into account. And I think that brings up risk dynamics again, and I think it really screams out the precautionary principle. Very good quote I heard recently. If there's a non-trivial possibility that the thing that we do will cause irreversible harm, the burden of proof should be on proving safety, not the other way around. And I can tell you that is not a common practice, not in policy, even in assessment. Assessment struggles to incorporate those things. So we're always trying to say, well, are we completely sure it's going to go, etc. But these, I think it's a really critical consideration. So take-home messages, I think, we need to be clear that the identified Earth system tipping point sensitivities already that we have identified are profoundly worrying. I think fuller inclusion of key metrics like interactive stresses, greenhouse gas levels and trajectories, Earth energy imbalance, super important, drives everything, inertia and overshoot dynamics, they're all likely to reveal greater tipping point sensitivities across a wide range of systems. I think the precautionary principle is absolutely profoundly essential when considering knowledge gaps and policy action. And we all need to engage with these issues. It's not something we can just leave to others because it will affect absolutely every citizen on this planet. And above all, it's got to inform mitigation policy. And I would just end with two key questions, I think. Can we avoid unmanageable Earth system impacts? I'm not even calling them tipping point impacts. Don't need that. You can see already that we're driving, hammering these systems so much that just linearly will actually go into a compromised state. Can we avoid unmanageable consequences? And if so, how do we do it? And I increasingly hear at things like COP, cryosphere, pavilion sessions and things, people will say, we can't prevent it now, but we can slow it down for humanity to deal with those coastal inundations and the rest of it. And if that's the reality, we are a poor bequest to future generations, maybe not that far off. So my challenge to people like Sir David is, can we actually do better than that? Can we get out of a situation where we just continue to have a real escalating situation that we truly can't cope with? That affects all of us. Thank you.
Thank you, Paul. That was extremely sobering and very powerful. We're going to move from the global to a bit more of a specific now. I think one of the great strengths of this institution is its ability to hold within it both living collections in which Paul works, our conservation and policy work, but also really top quality world-class science. But not only in our Institute of Zoology. Dr. Chris Yesson has been at ZSL as part of the Institute for 15 years, doing really world-class science that is helping fill out the detail that we need to understand the impact of the things we're talking about this evening. He's been working to map life on the seabed from the tropics to the poles. But where I think he has really become the expert is in the seabed of Greenland, and in particular, the impact of climate change on that seabed. We're really glad to have him, and his work has part of ZSL and part of our contribution to this debate. Chris, over to you.
You'd never guess from that I used to be a management consultant. So I'm going to kind of take that kind of broader view that Paul's been talking about and focus in on coral reefs and what we know about coral reef tipping points, so the things that are going to dramatically impact corals. And this is really building on or reviewing the publication that Paul and I and many others have just had published, which is kind of reviewing what we know about the stresses of corals, what we know about the tipping points on coral reef systems, and importantly, how they interact with each other. And this is a spin-off or a drill down on the Global Tipping Points review that covered many more things and corals in brief. So I'm sure many of you know that coral bleaching is the kind of primary observable negative outcome for corals, and there's a really well-established link between temperature and bleaching activity. So bleaching is when symbiotic algae that within the corals, for reef corals, they depend on that algae for food. When we have prolonged exposure to excessively warm temperatures, so +1 degree above a kind of summer maximum, then we see this bleaching effect. The zooxanthellae, the symbiotic algae, leave the corals, and then we get this bleaching effect, so the corals look white. There have been 4 global scale bleaching events that have occurred in the last 25, 30 years, most recently last year. This is a map of the tropics showing that pretty much every part of the world has been impacted by bleaching, some areas worse than others, but nowhere has come off unscathed. So the bleaching and the link to this kind of extreme temperature, it has been related to the kind of global temperature rise. It's not surprising that we have more extreme events if the kind of baseline temperature is warm. And so there's been a lot of work reviewing what is the impact on corals at different temperature levels above our kind of pre-industrial baseline, which here is at 0. So we have well-adjusted corals at this kind of baseline. At the point we get to about plus 0.7 degrees above that baseline, we see large-scale bleaching starting to occur. At the point we get to 1 degree above that baseline, we see mass bleaching and mortality. At 1.2, this is the widely recognized kind of tipping point threshold. Above this, we're going to see very, very high impacts and very high risk of impact. At 1.5, we're talking about irreversible phase shifts. And by that we mean, the coral reef system is no longer there and it gets overtaken, it gets replaced by systems like algae. And at 2 degrees, we expect 99 to 100% loss of coral reefs. Okay, and these numbers are here because these are the numbers that we're thinking about now as possibilities. And well, where are we? Well, we're probably somewhere between the 1.2 and the 1.5. Last year we kind of formally crossed a 1.5, but maybe that's a 1-year anomaly. We don't really know yet, but we're certainly above the 1.2 degree, which is this tipping point as we understand it for corals, and we have seen multiple mass bleaching events now. It's a really kind of grim. But temperature is not the only stressor on corals. Here's a nice infographic from the US agency NOAA, which summarizes a few of them, not just the warming ocean, but we see sea level rise, we see an implication of sedimentation, sediment in the water settles on the corals. We see more storms. Those storms create physical impact on the corals, damaging them. We see change in precipitation, more runoff from terrestrial environments, bringing with it more pollution. We see changing currents. That's going to change local temperature regimes. And we see ocean acidification. And I'm just going to talk about a couple of these stressors now, just to kind of show how they interact with each other and a little bit about what we know about them. So ocean acidification. So as we put more CO2 into the atmosphere, that CO2 exchanges with the ocean, creates a more acidic ocean. The pH decreases. That changes the concentration of calcium carbonate, which is the material that corals use to build their skeletons. And at some point called saturation horizon, that concentration gradient is no longer in the coral's favor. They have to expend energy to take that calcium carbonate out of the water, and at some point, a tipping point, they can no longer do that, and the corals can no longer build their skeletons. There's a lot of work. Chris Cornwall, a co-author on our report, has done a lot of work looking at this. And here are kind of 4 examples on the left. Blue essentially means a decent amount of calcium carbonate in the system and the ability to kind of bring that into corals. As you move across to the right, we get further into the future with worse emission scenarios. So on the right-hand side is RCP 8.5, really bad emission scenario, and we can see no blue. So essentially, the corals are going to be in a bad position where there's not going to be the calcium carbonate available to them to be able to build their skeletons. A map on the right top is present day. On the left are progressively worse emission scenarios for 2050, and on the right for 2100. Red is bad, green is good. And you can see that there's nowhere in the world that won't be really negatively affected by this. But this work done by Chris was back in 2021, but last year he published this new work, which I found even more alarming in that work was done assuming, not taking into account other factors that are negatively impacting corals. But when you factor in the metabolic effects of temperature stress, so one other factor, then the situation looks far worse. And this kind of idea that when we start to consider multiple stresses at the same time, we end up in a much worse situation. So another stressor story is disease, and this work is focused on the Caribbean, which kind of in terms of the kind of global coral perspective, we've seen a greater impact of disease in the Caribbean corals than anywhere else in the world. And we've seen a successive wave of diseases really impacting Caribbean corals, starting back in the mid-70s with white band disease, and then through to the present day where we're seeing stony coral tissue loss disease, as in the pictures. And this nice graphic from this publication shows that the composition of corals have changed over the last 50 years in the Caribbean, and also the kind of scale and scope and functionality of these have dramatically reduced. Now, at present, the Caribbean has been the center of disease problems for corals. Some people have suggested that primary loss for corals in the Caribbean has been disease, but that may not stay the case. Now, when we think about linkages with other stressors, we know that disease is impacted by other factors like pollution or invasive species acting as vectors for new pathogens. We know that increased temperature increases the risk, infection risk for many diseases, and also physical impact on corals makes them more vulnerable to disease and infection as well. So lots of other stressors are impacting and potentially causing a bigger problem for the disease issue. But I just wanted to kind of show this a very cartoony example that shows that it's actually a complicated picture for stressors. So on the left here, we can imagine, we know that corals are getting too hot, essentially, when you boil down to it. But there are potentially factors that might ameliorate that. So as sea level rises, the corals are in slightly deeper water is cooler. We get some pollution. Not that pollution's a good thing, but it can have a shading effect in the way that we see people shading corals in more vulnerable areas. But that potential positive impact can quickly switch into a negative impact where, maybe the sea level rise is too great or the pollution is too great, and then we flip into a negative impact. So it's not really very simplistic that, that even the kind of positive interactions might stay that way. So one of the things that we did with this review was look at the comparison, the linkages between different stressors, and this kind of little graphic, red lines mean these stressors are linked, and they are linked in a way that creates a worsening effect. There's a couple of blue lines on there, and the blue lines are kind of like the sea level rise temperature thing where we have a potential positive effect. But the fundamental is lots of these stresses are connected, and most of them are connected in a bad way. And what we know about tipping points of these stressors and their kind of scale and scope are really been focused on looking at that one stressor and not really thinking about the combined impact of these other stressors. And that's really the kind of conclusion of our paper, where we kind of think that we need to consider the potential negative impact of stresses in combination. And as Paul was saying earlier, it's important that we think about the precautionary principle when it comes to that approach, that we kind of don't know these combined impacts and they might not be good. So with that, I will wrap up and say thanks to the co-authors and leave you this lovely picture of the Tiny Giants coral tank based on a 3D reconstruction. Thank you.
Thank you, Chris. That was absolutely brilliant, and God, it was depressing. One of the things that I think ZSL does really well is the hinge between science and conservation, making sure that our conservation is evidence-driven and science-driven, and in turn our science and our science team have a sort of umbilical connection to what we're doing in the field. It's a very powerful combination. Rachel, our next speaker, lives that. She heads the Bertarelli program of marine science for ZSL, which is a huge, long-standing, really impressive program of science and conservation across the Indian Ocean. For me, Rachel's work is both built on and contributes to really impressive and important science. It's directly impacting conservation plans, conservation across the Indian Ocean. But as important is the way that she leads this work. It is done in a really inclusive, appropriate, respectful way, where Rachel has gone to enormous lengths to make sure that it is locally led, that we are empowering local leaders, bringing on young conservationists from the regions in which we're working. Rachel, we're looking forward to hearing from you.
Thanks. Okay, so when the future is scary and uncertain and as bleak as some of these pictures are suggesting, sometimes it really helps to just do something. So I'm going to take you now to a very specific set of coral reefs where I've been working for almost 20 years and talk about some of the practical hands-on things that ZSL is involved with to try and head off some of these worst impacts that we're seeing as the reefs change. So as Matthew said, I work for the Marine Science Programme, and we are a group of over 100 scientists from 24 institutions, and we have projects spanning disciplines, taxonomic groups, different habitats, and you can see we span across the entire Indian Ocean basin. But these projects all overlap in one place, and that's the Chagos Archipelago in the central Indian Ocean, you can see there. And that's because this provides us with a really interesting study site. Chagos is in the news all the time at the moment for political reasons, but just taking us back to the place itself, we've got over 60,000 square kilometres of coral reef spread across this huge archipelago. The biggest living coral atoll anywhere in the world is the Great Chagos Bank at the heart of it. And despite being immensely remote from big centres of human population, it is biologically speaking very well connected to the rest of the Indian Ocean, particularly to the west, by highly mobile species, by migratory species, but also downstream reefs to which larval corals can come from spawn in Chagos. So it's linked right across the region. It's globally significant for those reasons, and we can look at the effects of the impacts of climate change through sea surface temperature rises, etc., in the absence of some of these big other stressors like coastal development and overfishing of reef fishes, which are confounding those issues, as Chris was just saying, in other places across the Indian Ocean. So for all of those reasons, it's a very interesting place to work. Now, I won't just repeat what Chris has said about mass bleaching events, but really almost since I've been working there, we've been watching the reefs in the Chagos Archipelago swing backwards and forwards between wipeout and recovery. It's almost walking this tightrope between huge mortality events, bleaching followed by huge mortality events, and then this recovery as the reefs, which are otherwise in a very healthy state, are able to start growing back again. So far, the gaps between these big events have been 8 to 10 years, and they've been more or less long enough for corals to recover. That means that newly recruited corals have enough time to become sexually mature, or damaged corals have time to recover their physiological resources that they need to be able to spawn. So those intervals have been long enough for us really to be able to catch up. And the sheer number of the reefs that are connected means that the patchiness of the mortality can be recovered from reservoirs of healthy corals. But it isn't a linear process. And in the last big bleaching event, well, not the last one, the 2015-16 bleaching event, we saw coral cover across 3 significant atolls drop really substantially. And even by 2018, we weren't seeing great recovery. The recovery was really slow, very patchy, and it took a while to get going. By 21, we were starting to see really meaningful recovery across all the sites we were surveying. But again, it was patchy, it wasn't complete. We were losing from the record species, some of them temporarily, some of them permanently. Even very relatively common, very conspicuous corals like Seriatopora hystrix, for example, were becoming extremely hard to track down. So that recovery isn't as complete as we would like it to be. Nevertheless, in 21, it was happening. But in 2023, we were looking ahead to later that year, and we were seeing the projections from NOAA as the temperature was building through the central Indian Ocean. We would expect to see the temperature rising through December and into the first months of the following year. That's really the hottest time of the year. But we also knew on top of that baseline increase in temperature, we were expecting an El Nino event, and that was going to push temperatures quicker, higher, and potentially keep them higher in the danger zone where corals are really likely to be damaged. So we were looking at projections at top left in January and then through to February, down to March and into April. And you can see that the NOAA alert level gauge is in a very visual way going up into the higher levels of alerts, which really mean that wide-scale bleaching is likely, mass mortality is very likely. Now, this was sort of spring, early summer of 2023, and this projection really, really scared us, because we've been working with this coral on the left here, Tenella chagius, for some years now. This is the Chagos brain coral. We've been working with this species for many years because prior to the post-15-16 bleaching event, this coral had disappeared from the record. We had divers in the water, hundreds of hours of diving, and nobody could find it. It had gone from being the 7th most common coral species observed in the archipelago to gone. So for a few years, we were seriously concerned that we'd lost that coral completely. I should point out it's endemic. It's not found anywhere else other than this archipelago. So to lose the population across this archipelago would mean to lose a species. But in 2021, we started to find the odd colony here and there. And by the time we got to 2023, we knew of fewer than 100 colonies in total, and almost all of them were here in this amazing atoll called Middle Brother. That's Middle Brother Island up at the top right, and this is the tiny little lagoon just offshore, and these knolls in the middle of the lagoon, around the base of these knolls, are pretty much most of the remaining population of Tenella chagius. So you just cannot get more eggs in one basket than this. This is obviously not where you want to be when you're dealing with species recovery. So we were faced with this incoming El Nino event and the potential for a catastrophic warming to happen. And with this tiny number of corals sort of trapped in this little lagoon, we were extremely worried that there was a chance of a complete species extinction going to happen here. So we leapt into action, and to cut a long story short, we're able to go out to the Chagos archipelago and to collect 12 individual colonies and bring them back to the aquarium environment, initially to the Horniman Museum in South London, and now that we also have a matching set here at ZSL London Zoo. So we've been working with these species now for a year ex situ. This is a very classic species rescue, create an ark, keep the species from going extinct. It's always the action of last resort for conservation. It's not where any of us want to be, but in face of the pressures this individual species was facing, we felt it was a necessary precaution to take. We've been very successful with this species. It is actually, as it turns out, incredibly robust in the aquarium environment and has been growing and developing. And on Saturday, we had some spawning. So this is not a blob. This is a very, very tiny 2-day-old Tenella chagius coral colony. So this gives us something to work with. We can work with the reproduction of this animal. We can start to get to control that reproduction. We can produce bigger populations. And we're working with a network of other aquariums. As I say, 2 collections now, the Horniman and us. We've got a 3rd set going to the Monaco Oceanographic Museum within the month. And then the next on the list is Aditio Oceanarium in Mauritius. So under the World Coral Conservatory Initiative, this is a network of aquariums and zoos around the world who are working with individual species of coral of known provenance and really treating them in the way that you would endangered species of other taxonomic groups. So we're collecting founder populations of a significantly diverse genetic origin that we know we can have a captive population for a meaningful length of time. And we're working to really get those populations spread across multiple communities and use research as far as we can to impact work back in situ. By being able to control the reproductive activity of a coral like this ex situ, we can look at some hands-on methods for affecting reproduction in situ as well. Now, I'm not going to pretend that these things are going to shift the dial on the imminent the imminent pressures that coral reefs face around the world. These are very reactive and relatively small-scale actions. what else can we do? Paul talked about chipping away at or whittling away at the resilience of coral reefs, and that was a very good image for me. So is there anything we can do to help those reefs? Is there anything we can do to confer some resilience back on those reefs? So another very practical approach to this is to look at the problem of invasive species such as rats, and invasive vegetation, and the effects that this has on the island reef interface. So coral atolls are very intimately, the terrestrial environment on the island is very intimately related with the reef that surrounds it. And what rats do is deter seabirds, and seabirds are an incredibly important nutrient driver of these coral atoll ecosystems. They're bringing in protein from the open ocean. Their guano fertilizes the soil of the island. Those nutrients go out onto the reef that surround the coral, and they have a huge impact. And that's a natural ecosystem, a natural nutrient pump for that ecosystem. Where rats have been introduced, they deter seabirds, and the solution is a very simple one, a gratifyingly simple one, to remove invasive rats from coral atolls, to restore native vegetation habitats such as native hardwoods and savanna for nesting birds, brings the birds back. That restores that nutrient pump, and it has a huge impact. Our programme has been able to build a really stunning body of science to back all this up, and I'd really encourage you to read some of it. Those two papers are a good place to start. There's a really compelling quantitative case for the impacts that rat eradication and habitat restoration has, not just on island ecosystems, but on the reefs that surround them. So that's a potential for something that can confer resilience on coral reefs. It may buy us some time. It may give the reefs a chance to a small extent, adapt to the situation they're in. But we shouldn't be under any illusion the face of the scale that these coral reefs are facing in terms of change. I think really the time to act is very much now. We've already lost about 50% of our coral reefs globally. The remainder are very much under threat. And we're walking this tightrope. We're right on the top of the tightrope now between a world with coral reefs and a world without coral reefs. We've got some tools and strategies that can head off some of the worst impacts that we're seeing, such as total species extinction or these ecosystem dysfunction that I was just describing. But it's really only the sort of rapid and permanent drops in emissions that are going to prevent the complete loss of coral reefs. So that's a future none of us want to see. At this point, I'll hand over to our main speaker of the evening. Thank you.
Thank you, Rachel. That was superb. And I think what ZSL did, what you did with the Chagosian brain coral was really extraordinary. Clearly, given the scale of what we're facing, saving species one by one isn't going to be a sufficient answer. But if every species lost is a tragedy, then every prevention of a species being lost is the opposite of a tragedy. And if you haven't yet seen the short film we put out on our rescue of the Darwin's frogs, strongly recommend it. It's a really beautiful and short film. Our keynote speaker this evening has been an absolutely towering voice and figure at the hinge between science and policy. I first met him almost 20 years ago when he used to come in to advise the then Foreign Secretary, David Miliband, on climate change. I think I was more affected by meeting him than he was by meeting me. But Sir David King became government chief scientist a quarter of a century ago, carried that very heavy burden for 7 years. After that, was the special representative for the UK for climate change. But almost more importantly than that and those jobs, and I think it's 22 honorary degrees and the formal record, is the unique role and voice that Sir David has carved out as somebody who wants the science translated into action and has wanted to both warn us, our leaders and the world of what it is the science is telling us, and has played a critical role in pushing global policy along, not just in the UK, but core relationships in other countries as well, to make sure that we are doing our best to sound the alarm and then to respond to the alarm. We're very honoured to have you here. Ladies and gentlemen, Professor Sir David King.
Well, firstly, Matthew, thank you for those very warm words. I don't often get introduced with warm words like that, so it's a real pleasure to be here. And actually, it's more than a pleasure. It's been a wonderful education listening to the speakers who've gone ahead of me. I really want to say this. My field is physical chemistry. I, in one sense, couldn't be much further away from what you guys are all experts in. And so this is the way that I've always learnt, by listening to people outside my direct disciplinary area. So thank you for those presentations, which were all amazingly good. I'm also astounded by the quality of your slides and the size of your screen. So I apologize in advance for what you're about to experience. I don't even know whether they're going to show up in any form that will look like slides. So I'm going to run through the global situation. Extreme weather events of an extreme nature are now common around the whole world. And there's been very, very little information given out by the scientific community to explain this. Now, I run this Climate Crisis Advisory Group, which is 17 individuals from 10 different countries, north and south. Those individuals are all well-known climate scientists. So we are a unique group of people, and we put out reports roughly every month. The difference between us and the IPCC is that we report in time. When things are happening, we report on what's happening. IPCC reports take about 6 years to appear, and it's a lengthy process. We're not responsible to any governments, to any companies, to anyone else. We are just a group of individuals. So this is just a picture showing the kind of widespread activities that we're now becoming, in a sense, quite used to. No part of the world has developed the resilience to deal with the current level of changes in the climate systems of the world. And there's one of the big question marks that we're addressing to mayors of cities around the world, to government leaders, to state leaders. For each part of the world, the challenges are now different to create proper resilience. These events won't calm down going forward in time. They'll only get worse. Now, let me just, I find this slide quite frightening. So what we're showing is the annual change of temperature compared with the pre-industrial level from January through to December. So this is month by month. It is showing how much the temperature has risen over the period since 1950. And then you look at these recent curves. 2023, spectacularly higher than 2022. Yes, it was an El Nino year, and you can see that we all thought that curve was going up and would then stabilize, but it's run into 2024, and look at January 2025. So I think Chris was saying, is this just a blip, or is it continuing? I don't think it's just a blip. I think we've got to face up to the fact that we're in a different world. That big leap that's happened is way beyond any previous El Nino event. And so this is already looking horribly like what we were hearing about tipping points, that the global climate system is somehow tipping. Let me try and give you an explanation for that. I don't have a lot of time, so I won't go into it in any detail. But just to say something about the cost of those extreme weather events around the world. So this is from that group that we've just heard about, who've been publishing extremely good analyses from the actuarial world of loss and damage already occurring per annum from these extreme climate events. Those cities that have been wiped out have a big capital cost associated with them. And by the way, this doesn't appear in the growth of economies, because economies actually grow when people rebuild cities. Economy isn't measured, GDP measurement doesn't tell us anything about the infrastructure that we've lost. It gives it a reverse view of that. So I'm just saying, let's now look at the loss and damage resulting going forward in time. This is the actuaries from London, the people who the reinsurance industry use to predict the loss and damage so they can charge the right amount for your insurance, right? So that red curve is their latest curve, and you can see the big error margins that they sit with. But these are people who are used to giving you an analysis on the possibility that your house will burn down. They have to analyze it carefully, and then they will give you a cost to insure yourself against that happening. Imagine the insurance industry looking at Los Angeles today and what they're trying to work out in terms of the cost. There will be non-insurable houses right around the world as a result of these events happening. But if we look at this in terms of loss and damage, looking at the actual infrastructure that we have, this is an enormous percentage that they're predicting going forward in time. I don't believe that we can go past 2040, 2050 without seeing this as a major turndown in our standard of living globally. Right? So, of course, what I'm looking at here is if the world carries on the way it is now. I'm not saying this is the world we have to adapt to. I'm hoping that we can change opinions and get some real progress. All right, so what I'm summarizing here is now simply the urgent need for climate action. January 2025, I've just shown you the data, but I didn't pinpoint that data point. That January this year was 1.75 degrees centigrade above the January average figure pre-industrially. All right, so, but now I just got some data in this morning from the 3rd of February. 3rd of February, the North Pole region was 32 degrees centigrade above the pre-industrial average for the North Pole region. 32 degrees centigrade. And the region around it down to 25 degrees centigrade above that pre-industrial level. And that's already an important piece of information. Why is this happening? Well, of course, it's the loss of ice over the Arctic Sea over that period of time changing the albedo. Right, so the reflectivity is changing from high reflectivity, sunlight hitting ice going back into space, to very low reflectivity when it hits the blue sea. And that blue sea, so let me tell you a little story. A member of our group, Tero Mustonen, I spoke to him, I'm going to go back in time to 2021. I spoke to him chatting on the Zoom in April that year, just said to him, what's your local temperature? So he's a member of the Sami group of people who live up on the northern Finland area on the permafrost. And he said, well, the temperature today is -30. He said, that's unusually low. It would normally be about -15, -10. Spoke to him the same year, July, a few months later. He said, you better be sitting down. The temperature here today is +32. 60 degrees centigrade temperature rise over a short period of time. So what's happened there was unusual, but it was easily explicable. Blue Sea, nearby to where he lives in northern Finland, Blue Sea producing warm air above it and an airstream carrying it straight over where he lives, +32. Now, of course, that's threatening that permafrost that he's living on, and what will that produce? We need to be looking at that. I think the basic message is no government is doing anything about tipping points. We're not seeing actions that are directed at anything but, and I'm not saying this is unimportant, stopping the use of fossil fuels. Right? So the total focus of the COP meetings is on end the use of fossil fuels and get to net zero by 2050, 2060. Some countries are saying 2070, India. So what about today and tomorrow? What about these extreme weather events happening now? What are we going to do about it? And that, for me, is the crunch point today, that we don't have governments focused beyond where we were in 2015, when we were simply looking at emissions of greenhouse gases into the atmosphere. We know that everything that's happening goes beyond the effect of the greenhouse gases. It's the loss of albedo as well that is a big, big factor multiplying the process. So here I have the history of climate science, and I like to spell this out because most Americans don't seem to believe that we knew anything about climate change until about 1960, because this is all European scientists working. We go back to Fourier, 1820. He was this wonderful mathematician who thought he could calculate everything, including knowing how much energy was coming from the sun reaching the Earth, how much the Earth was putting back into space. He knew that a hot body produced infrared radiation in proportion to the fourth power of its temperature. So I can accurately calculate the surface temperature of the Earth when that balance is achieved, energy in, energy out. He calculates it and he doesn't publish what he got. He gets initially -30 degrees centigrade. He knew that was a bit low. And so he recalculates by putting in what we might term a fudge factor to get the right number. And that fudge factor, he said, was because radiated heat from the Earth's hot surface was being captured by the atmosphere. The atmosphere was acting like a duvet over your bed at night, capturing your radiated heat. Along comes the great Irish scientist, actually, Tyndall. Tyndall actually measures that random coefficient that was used. It wasn't random. He was getting the right number as a result of making that coefficient what it was. He finds almost exactly the coefficient that Fourier had to put in to get the right number. So he measures this. You take a tube, you put air in it, you put a warm body at one end, and you see how much heat comes out the other, and you evacuate the tube and see how much heat comes out the other. So he works it out. Fortunately, he repeats his experiment twice. The first time, he cleaned the air, which meant he was just left with oxygen and nitrogen, and he got 0 infrared radiation absorbed by the oxygen and nitrogen. Diatomic molecules, which are symmetric, same at both ends, have no dipole moment. They can't capture infrared radiation. This was the discovery of greenhouse gases because he repeats the experiment with air as it's taken, with water vapor and carbon dioxide in it, and that's the discovery of the greenhouse gases. 1860, we have that. 1898, one of my top favorite historical scientists, Svante Arrhenius, Nobel Prize winner 1902, he says, wait a minute, I can use these equations to calculate if we keep burning fossil fuels, what would happen if we doubled the amount of greenhouse gases in the atmosphere? And he comes to that figure of plus 5 degrees centigrade. This isn't a piece of new science. This has been around for a long time. And if you want to know what the computer modelers modeling climate science do, they use these equations. Today they use these equations. That's the basis of it. Now, of course, there's another group of people really outstanding, who are looking at paleoclimatology. They're looking backwards in time to see when the Earth was last, for example, at the current level of greenhouse gases and what the temperatures were like then and what the planet looked like. So there's this comparison between paleoclimatology and the calculations. Now, unfortunately, the calculations haven't adapted to all of these positive feedbacks, tipping points, and so on. But the paleoclimatology data does show it. If you really want to look at important stuff, read James Hansen's recent papers. There, it's all spelt out in detail. So basically, this is just running through where we are today. Greenhouse gas levels. If you look at just carbon dioxide, which is, I'm afraid, what the IPCC tends to focus on, actually does focus on, today 430, 427, 430 parts per million. But add in the methane. Methane levels are rising very, very rapidly now. The loss of methane from all the recovery of coal, oil, and gas, but also increased consumption of meat by human beings is producing more methane. So what we're looking at in total is over 500 parts per million today, the pre-industrial level 275. We're rapidly approaching doubling the greenhouse gas levels, doubling the amount captured by the atmosphere, and therefore we see rapid climate change occurring. And here's the temperature rises across the globe. This just emphasizes with the maps above that the temperature rise is far from constant around the world. No surprise there, but in particular, look at the North Pole region, where the temperature rise has been for the last 5 to 10 years, 4 times higher in rate of increase, but it's increased again more recently. I'm just going to show the updated version of that temperature curve going to the 2024 figure and see that rise up to over 1.5, and now we know hitting 1.75. So here's a simple picture to explain what I think is really critically important. We know the rotation of the Earth produces this wind up in the stratosphere, starting in the stratosphere, coming down to the jet stream in the lower atmosphere. And that jet stream would historically be almost circular around the North Pole. But it has it's been meandering as a result of what I believe is happening. The higher temperature around the North Pole region chasing the cold air down and pushing cold air right down. The Dallas in Texas experienced temperatures of 49 degrees centigrade, and Americans had no idea what was happening. It was the distortion of that jet stream. We pictured the jet stream at that time and could say, look, that was why. The hot air being the cold air coming down, hot air coming up, because the atmospheric pressure has to be balanced. So where cold air has come down, hot air comes up from the equatorial region. You will remember that in that year 2021 that I mentioned, and we produced a paper on this at that time, 2021, up in Canada, the town of Linton, suffered a temperature of 49.5 degrees centigrade for about 10 days. 135 people died of heat stress in this upper middle class town because Canadians don't have air conditioning. Right? There was no preparation for a temperature of that kind. So this was hot air coming up due to this meandering of the jet stream all the way up the west coast of America to Canada. And they had this, the jet stream got stuck in that position for that 10-day period. The town finally burnt down because the local forest caught fire and the town was destroyed. So it's important to understand that what is happening in the Arctic Circle region is impacting on the weather systems of the whole world. So here I'm just adding together the challenges. That high temperature being experienced on February 3rd this year laps right into Greenland, right? So the molten ice is producing hot air right along the coastline of Greenland, the east coast. Now, Greenland is now losing ice at 30 million tons an hour. Now, believe it or not, I think that's an irreversible factor. We're looking at this occurring over the last 10 years as an average at 30 million tons a year, an hour. Yeah, 20 years ago, it was measured at 50 million tons a year. So there's an onset of rapid melting. When all of Greenland ice has melted, we know sea levels will have risen by 7.5 meters, 24 feet, but that is going to play out over a longish period of time. But as one of your colleagues said, 1 meter, 2 meters, that's enough to upset the whole world. It's not going to continue in the current global economic system at that sort of level. Vietnam, that country is so close to sea level that we're currently predicting it will be 85% under seawater at least once a year by the year 2050, just 25 years from now. That's the third biggest rice producer in the world, and that'll be the end of their rice production once that area is salinated. So we're looking at impacts across the world that are unimaginable in a way. All right, here's the big positive news. The falling costs of energy systems, land-based wind, PV, etc. It says since 2008. I made this slide in the year 2015, but I'm showing it now because many people believe that shifting away from fossil fuels is going to cost us in terms of our GDP growth. I don't believe that's true for almost any country in the world because of this fall in the cost of the new energy systems that were competing originally with the fossil fuel systems that were fully mature. These were new technologies coming in, and as they matured, the cost per unit kilowatt hour has been reduced massively. Look at light-emitting dimers. They've not only come down in cost, but as with all the others, improved in efficiency as well. So there's not a city in the world now that isn't lit with light-emitting dimers. Massive energy saving in that. So this is just saying, how did this happen? Well, I'm prepared to put my hand up, along with the Blair government, introducing feed-in tariffs in the form of a demand on all of the electricity companies to put a certain percentage of renewable energy on the grid with penalties if they didn't do it. The utilities didn't mind because the cost was passed on to the public. You paid a little more for your electricity. A little more because originally it was only 2%, then a few years later 4%, then 6%, and so on. So the percentage of renewables was increased over a period of time, but the cost was coming down. And this spread across Europe, Italy, France, Germany, etc., right across Europe, and also into California. So what we saw as the market expanded to meet this new demand, the cost came crashing down. Now this slide was done before China came into the game. And once China came into the game, these prices all crashed down again. Right, so what we're looking at today is the cost of energy production from these is really dramatically less than it was 20 years ago. So I come back to the critical pathway that the Climate Crisis Advisory Group has been pursuing for 3 years now. We call it the 4R Planet Strategy. May sound a bit corny, but it's a means of remembering. We've got 4 Rs. The first is, yes, we have to reduce emissions deeply and rapidly. I'm now involved once again in traveling around the world to persuade every government to announce a major change in their own ambition to reduce emissions. And I think we have the first success in the United Kingdom with that 81% by 2035 promise from our Prime Minister in Baku on the first day of the COP meeting last year in Azerbaijan. And what I'm actually saying is that's only the first. Where did this come from? It was an idea cooked up when I paid a visit to China. China's doing probably more than any other country in the world to shift away from fossil fuels, whatever anyone says. And we decided what we needed to do was get individual countries to make these statements before the COP meeting in Brazil this year. We've got on board the United Kingdom, European Union, France, and this was the work of my Chinese colleague very heavily. And I'm off to South Africa in March, talking to the Indian government. Brazil is on board. So what we have is a group of nations, and we're hoping to get a groundswell who can announce a dramatic improvement in the shift away from fossil fuels. And the whole point I want to emphasize is it's going to be cheaper. Now, of course, when we talk to India and South Africa, they say, but we've got loads of coal in the ground in South Africa or in India, and we've got a lot of workers working on removing that coal from under the ground. Do you want us to put them out of work? I had to address the trade union movement in South Africa, the coal miners. They said, Comrade King, they call me Comrade King because I was kicked out of South Africa in the apartheid period. You are telling us that we should stop working. I said, no, I'm not. I'm telling your government to retrain you, to put solar panels, vast solar panel arrays in the Kalahari Desert. Use the labor to manage that process. So we're now talking very sensibly to South Africa. In India, Modi is currently saying, I can't touch the coal miners. So it comes down to very nitty-gritty issues which are important when you're talking about democracies in particular. Very, very difficult for people to stick their necks out and make key decisions. But the second R is remove. What we have to do is remove excess greenhouse gases that are already there. There are still governments talking about there's a carbon budget, isn't there? We can still put carbon dioxide in the atmosphere because 2015, the IPCC told us there's still a carbon budget we can spend. There is no carbon budget, 500 parts per million. My belief, and I know that I'm picking the heads of the leading scientists in the world when I say this, is we have to bring that down to less than 350 parts per million in total to have a manageable future for humanity. Now, how do we buy the time to achieve that? The first two are going to be rolled out over a long period of time. We haven't yet established basic techniques that will remove excess greenhouse gases safely and bring them down to that level. We're messing about with direct air capture, massively expensive processes which seem to do the trick at a very low level. We have to establish techniques that will remove tens of billions of tons of greenhouse gases a year in order to achieve this. Is that doable? I believe it is. And we need the enterprise, the research to be put into that. Repair. What do we do about the North Pole? Let's just focus on that. Not an easy question to answer. We all know there's a lot of skepticism being raised about people calculating how we might reduce the amount of heat reaching areas of the Earth's surface by putting, for example, sulfates into the stratosphere. Now, I've set up a group who are working on developing white cloud cover that would only be put over the North Pole region during the 3 polar summer months, right? So that we can keep the ice that is formed there in the winter through those 3 polar summer months. Now, you will already see the catch in what I've just said. 3rd of February, we're losing a vast amount of ice in the Arctic already. So what I believe is now happening is the warm ocean currents are coming right up into the North Pole region and keeping it warm during the polar winter months. There's no sunshine there, so it is the sea, the ocean that is doing this. We need to work hard on possibilities of repair to buy time to allow us to achieve the first 2 R's. The 4th R we have to do anyway, create resilience in every part of the world. Now, I think I've said my bit. We're in a critical situation. The positive message to emerge, if I can call it positive, from all of the speakers today, is that tipping points are with us. It's not something we're talking about in the future. Tipping points are with us. How do we manage? Well, I do believe it's a challenge to the scientific community to stand up and say, this is what we have to do. We can't sit back and say, this is all going to happen. We really have to, with clear resolve, take these messages to the political community. And that's me working at that interface between science and politics that you mentioned, Matthew. So I leave you with that, but I look forward to a good discussion.
Thank you, Comrade King. Could I invite you and the other speakers to join us? We will have time for a brief question and answer, but hopefully we'll be able to get through a few questions if questions and answers are brief. So I have 1,000 questions, but I'm going to resist the urge to ask them. We'll go to the audience.
Thanks very, very much indeed to you all and for some amazing talks. And I was especially sort of bowled over by the one by David King. And it's to you I'd like to sort of put a sort of question, which I'll try and keep brief. You put up one of that slide which showed the massive decrease in GDP by these catastrophic events that are happening. But you also sort of alluded very briefly to the fact that our economic system is actually benefits by those catastrophic events because it sort of generates GDP. Given the fact that we're so short of time in trying to turn things around, we get a lot of rhetoric from politicians about what they're doing. Do you think that one way we could really accelerate the whole process is by changing the way that we measure our sort of well-being or our economies?
Well, I love the question because I haven't, until this moment, had a chance to say, we need a cultural revolution. And in that cultural revolution, we need to look at people, climate, biodiversity. We really, and the last one, nature. We have an economic system that gives zero value to the systems that are now being massively challenged. Zero value. That economic system, you're able to treat the ecosystems of the world as your rubbish bin. And that is what is happening. So I do think you're raising a critically important question there is one part of the world where this is a very real discussion, where there is a global ecosystem meeting. And that meeting is attended by 9,000 to 10,000 people every year. It's in China. And the Chinese government has now written into its constitution the need for us to move into an eco-civilization. And they define eco-civilization as a system in which we give equal priority to the well-being of our ecosystems and to the well-being of human beings. Now that's an easy thing to say. It's one hell of a challenge to shift from our current system to that one. But I think you're asking the right question, and then I'm faced with this enormous challenge. How do we bring about that sort of cultural transition? It may happen in China, but can it happen in the rest of the world? Because the whole world has to follow suit.
Thank you. We'll go to the lady just behind. Thank you.
On the radio this morning, they were saying that Shell and BP are going to reduce the amount of new technology and getting away from fossil fuels and move back to extracting more fossil fuels. How do we get the message across to those sorts of companies that surely climate change is going to impact their ability to extract oil and gas, because surely the land and the sea are going to be affected by climate change?
So more fossil fuels obviously is the name of the game for President Trump in the United States. But I just want to say this. It's not a dramatic transformation in the United States. The power of the US fossil fuel lobby has been the biggest challenge I have had over the last quarter of a century. That fossil fuel lobby has been pushing this so hard that last year, even with the Biden administration there, the United States produced more oil than they or any other country in the world has ever produced. Right? So what we're looking at is politicians saying something and doing the opposite. Trump isn't saying the opposite, right? So at least maybe there's an element of honesty there. But I mean, obviously, this is the most damaging position to take. I've been talking to fossil fuel companies for very many years, became very close friends with John Brown, who was then CEO of BP, and he changed BP from British Petroleum to Beyond Petroleum. And then the board sacked him. So the point is that oil companies are in the business to make money for their shareholders. And that is a tough call for them to then switch away to other business because that's not their speciality. The real answer to your question is we have to curb demand. The demand side has to be dealt with. Those companies will keep producing oil as long as the demand is there.
Very quick question, just going down the line. If everyone here were the leaders of the world, what's the one sentence you'd be saying to them?
Oh. Is it all one sentence? I think I would repeat what I've just been saying to you. I think the point I'm really keen to get across to every government, and in China, we said, yes, you're doing a lot, but not enough. And they put all of our comments onto the front page of the national newspapers. Right? China really listens to what you're saying. I'm going to be saying the same in South Africa, same in India. Every time we talk about the issue, you've got to get across the message. Humanity's future is at stake unless you take action.
Paul.
Yeah, well, do your job. Yes, you're elected. They will do what we demand. And that's why I think it's our collective policy influence and power that can hopefully yet save the day, personally.
Thank you. Rachel.
That climate and biodiversity loss are the same issue. It's one issue, and to view that as a single problem to solve.
Thank you. Chris?
And following that is the importance to push for restoration as part of that message, to say, there's lots of good outcomes from, restoring seagrass habitats from a kind of carbon perspective as well as a biodiversity perspective.
Thank you. Chris, Rachel, Paul, Comrade King, thank you very much indeed.